Okay, hello everyone. Welcome to our first Stanford first paper reading group series on YouTube. Very excited to have everyone here. Again, I just want to emphasize that we really take an approach where no question is too small. Feel free to ask questions as much as you want throughout, and we'll try our best to get them answered. We're really excited to have Danfu with us today. Danfu is a fifth year PhD candidate at Stanford. He's the organizer of the Stanford MLSys series on YouTube. And he's also co-author of FlashAttention, along with many other great works at the intersection of machine learning and systems. Really excited to have Dan with us today. I won't monologue anymore. I'll hand over to Dan. But again, please feel free to ask questions throughout, and we can, take it somewhat discussional. But yeah, over to you, Dan.
Cool. Thanks, Dan, for the great intro. So like Dan said, my name is Dan. I'm at Stanford, and today I'm going to be talking about our work on FlashAttention, fast and memory efficient exact attention with I/O awareness. This is work with a lot of great people like Atri, and my advisor, Chris. All right, so the high level point that we want to kind of get through about today is that in FlashAttention, we introduced a new way to compute attention that focused on reducing the amount of memory I/O in the attention computation. As a result, it yields speed, memory saving, and quality. So it's a fast algorithm. It's memory efficient, which means you get the memory footprint grows linearly instead of quadratically. We used FlashAttention to get the fastest BERT on cloud instances in MLPerf 2.0. And allowed us to train transformers to much longer sequences, up to sequence lengths of like 16.4K, this was a little over a year ago, to yield higher quality on a lot of downstream tasks. Since we released FlashAttention about a year ago, there's been massive adoption. It is now a first-class operator in PyTorch 2.0. OpenAI used it to train a bunch of their models. Meta used it to train a bunch of their models. Folks re-implemented it in JAX. We used it to speed up stable diffusion, and it's kind of sort of everywhere now. We've been kind of very humbled and excited by the adoption since we released it. The motivation for us really in exploring FlashAttention was we wanted to be able to start modeling longer sequences. So in text, what that means is that you can have kind of larger context to understand more context. So this is, if you talk to people now, this is kind of obvious, but about a year ago, context length was not really a major battleground in kind of foundation models and language models. But now we know that longer context allows you to do things like understand books or plays or instruction manuals, and use that information to kind of answer questions. We were also excited kind of about non-NLP applications. So in computer vision, we think of longer context as being able to close the sort of reality gap. So in computer vision, longer context usually means higher resolution. So that can lead to better, more robust insights. Long context also is very important for different modalities where that are more naturally modeled as long sequences. So for example, time series are naturally modeled as sequences of potentially millions of steps. Audio sequences are most naturally modeled as kind of high resolution waveforms. And the ability to process long sequences is really important for a lot of these applications. So the challenge we wanted to address in FlashAttention was how can we scale transformers to longer sequences? Since we released FlashAttention, we've kind of explored some of these downstream applications for long sequences that are very exciting. So this is one from one of our collaborators, Ermon and Thomas, who used FlashAttention and transformers to build kind of foundation models for brain decoding. So here the inputs were fMRI sequences, and the long sequences were very important to get the fMRI information. It's also useful for kind of high resolution MRI. So here's a example. Medical applications are really interesting for high resolution because if you kind of do the standard computer vision thing of down sampling your image, you will actually lose the details that tell you whether there's a pathology. So for example, you can see on the right, those little boxes and tissue segmentations, the difference between a pathological, in this case, I think this is the knee, difference between something wrong with the knee and something, and kind of a healthy knee is kind of very small. And if you imagine you downsample the image on the right, then you can actually lose a lot of those details. There's a similar story in kind of histopathology. So here, here's a great example of looking at kind of tumor lesions from a histopathology analysis. And here, you really want to be able to do things like look at the tiny details in these massive gigapixel images. So that's kind of some motivation about why long context is kind of interesting and important. So the talk will be split into 4 parts. So first I'll give some background kind of about attention, about the attention computation, so we're all on the same page. Then I'll talk about FlashAttention, and then our empirical validation. Finally, I'll end with some future directions, chatting a little bit about kind of algorithms that go beyond attention, and some of our more recent work since we released FlashAttention a year ago. So I'll start with some background on attention. So I'm sure kind of everybody in the audience is familiar with attention, but I'll just go over briefly so that we're all kind of on the same page in terms of notation and everything. So attention is really the core computation that's at the heart of transformers. So you can think of a transformer as a stack of these encoder blocks on the left. And in each encoder block, you take an input, project it to Q, K, and V, which I call that for historical reasons from the Attention is All You Need paper. These Q, K, and V go into this attention block, this green attention block. You get a single output out, and that gets sent to the MLP, which then goes to the next layer of the encoder block. So let's dive a little bit more deeply into the attention block. So here I'm showing kind of the operation on a single attention head. Usually in transformers, you will have multiple of these blocks running at the same time. So these inputs, these Q, K, and V, they're going to have a shape of n by d. So you can think of this n, this capital N, as the sequence length. So you can think of that as 1,000 or 2,000, depending on your transformer, or these days, 8,000, 16,000, 64,000. This lowercase d is the attention head dimension. You can think of this as 64 or 128. So you should think about the inputs and outputs of this operation as these long and skinny vectors. So what attention does is, What attention does is you take these Q and these K, and then you take this kind of Q times KT operation. What that does is it gives you this n by n attention matrix. So what that means is now you've gone from these long and skinny n by d to this very large fat n by n matrix. Typically, you'll then apply some series of operations. For example, masking. This is showing what a key padding mask may look like. Then you apply a softmax operation. Then you apply kind of pointwise dropout. At the end, you have another matrix multiplication with this other long and skinny V vector, this n by d, and the output is again long and skinny. So the key thing to recognize here, there's a couple key things. So first, because you're computing this n by n attention matrix, you're gonna have compute and memory that's quadratic in sequence length. So the compute is because you have to kind of compare every one of these n by n things to each other. The memory is because if you just write this down naively in standard PyTorch, you have to write down and carry around this n by n matrix. And you have to apply a masking operation or a softmax operation or dropout operation to this n by n matrix. So as a result, you get memory that is quadratic in sequence length, and that bottleneck kind of makes it slow and hard to scale to long sequences. In FlashAttention, what we're going to do is we're going to replace all those bits in the middle with a single fused CUDA kernel. So your inputs and outputs are going to be these long and skinny matrices, and so the only thing that goes to GPU memory is these long and skinny matrices. Okay, so the other thing to notice here is not only does naive attention have kind of this quadratic memory footprint, that's actually going to be the source of kind of most of the runtime. So in particular, it's bad that you have this quadratic memory footprint, but every single one of these operations I've just drawn a little box over, if you think about kind of the flops involved, it's very small. Like the flops of masking, basically non-existent. The flops of computing softmax, very small. The flops of dropout, you could basically count it as almost nothing. But each of those operations requires reading and writing this n-squared matrix to and from GPU memory. So the naive implementation requires repeated I/O from the GPU memory. So GPUs are really great, really kind of well-engineered these days. They have very fast, high bandwidth memory. But compared to the amount of arithmetic that you're doing relative to how much you're reading and writing, the naive implementation requires a lot of I/O. We would say that it has a low arithmetic intensity for those of you who are familiar with that term. We're not the first people to notice this. There's this great paper called Data Movement is All You Need that talked about how moving these matrices around was really a bottleneck in attention. Yeah, and what we do in FlashAttention is we're going to, because we're eliminating all these reads and writes from GPU memory, because we're never writing down this quadratic matrix, we are not only reducing the memory footprint, we're also reducing the amount of memory I/O, and we're going to move to a more compute-bound scenario where, because we're not having to write these things continuously, the entire operation is going to go a lot faster. So just to briefly cover again, kind of the GPU memory, compute model and memory hierarchy. You see on the, yeah. So the one thing to recognize about kind of GPU, the GPU memory hierarchy is that there are these multiple layers of GPU memory. So if you look on the left, we have kind of multiple GPUs. This can be, you know, your 8x A100 box. Each GPU is going to have some amount of HBM. That's that thing in green. That's what you see when you type in NVIDIA SMI and it says 40 gigabytes or 80 gigabytes. And then each GPU has these compute units, so these little blocks in dark blue that are called streaming multiprocessors for GPUs. You know, TPU has a similar model. These streaming multiprocessors are really what can do the actual computation. That's where the actual kind of like compute unit is. And they have this small amount of this thing in orange called SRAM. So if you remember from kind of your basic intro systems course, there's these memory hierarchies all over computers. Like on a CPU, there's DRAM versus disk. You can also think of like kind of disk versus network, where generally the bigger your memory store, the more memory, the more stuff you can store, but the slower it's going to be. So if you imagine, you know, the cloud network, you can store basically anything on the cloud these days, but downloading it from the cloud is very slow. Likewise, you know, my laptop has a disk of a few terabytes, but it's going to be slower than DRAM. And then DRAM, you're going to have hundreds of megabytes, hundreds of gigabytes, but that's going to be a little bit faster than disk, but it's going to be slower than on CPU than a cache. When we get to the GPU, for example, a 40 gigabyte A100 has 40 gigabytes of GPU memory that has a bandwidth about 1.5 terabytes a second. And then when you get to SRAM on an A100, for example, you have about 20 megabytes per GPU, but it can go kind of 10 times faster at 20 terabytes a second. So you're seeing an order of magnitude speed up, but 3 orders of magnitude smaller. So with FlashAttention, what we're going to do is we're going to exploit this memory asymmetry to get speed up. So we're going to look at the I/O complexity and kind of using I/O awareness, we'll be able to account for read and writes to different levels of memory. And we're going to exploit that little bit of GPU SRAM at the top to speed up attention. So there's kind of some background on, some additional background. There's been, some work on trying to kind of just reduce the memory footprint of attention. So there's this paper called Reformer from 2020 that traded off kind of a more memory efficient attention computation for speed. So the trade-off was they're going to compute attention one row at a time. And that reduced the amount of memory footprint because you only need to just kind of store one row of the attention matrix, but it was a much slower algorithm. There's this great paper by Rob and Stotz from 2021. It said self-attention does not need n-squared memory. And again, this was another paper where they traded off memory footprint for speed. So here our algorithms were still pretty slow, but they were more memory efficient. In FlashAttention, we're going to try to get both speed up and memory efficiency. There's also been a lot of great work on kind of approximate attention. So do you need to compute this whole n squared thing? There's been a lot of work kind of in our lab about this, as well as kind of out there broadly. So there's kind of sparse attention, low rank attention, and these algorithms kind of trade off quality for higher speed. In FlashAttention, we were really wondering, can we avoid this quality trade-off? Is there a fast, memory efficient, and exact attention algorithm out there? Speaking of, we'll now get into FlashAttention and how we actually achieve that. So fast, memory efficient, and exact. So what we did is we said, okay, we're going to figure out how to compute attention block by block. And what that allows you to do is you only need to kind of write one of these blocks to HBM at a time, and you don't actually need to store the whole attention matrix. So we're going to use kind of a well-known algorithm kind of from systems about how you compute these n-squared things called tiling. So we're going to restructure the attention algorithm to load it block by block. So one challenge is that attention has this softmax computation in it, which naively requires having the entire row of the attention matrix. So we'll talk briefly about how we overcome that challenge. The other challenge for deep learning in particular is that typically you need to store the entire attention matrix from the forward pass in order to use it in the backward pass. And in FlashAttention, we're just going to recompute that. So we're going to store a few little bits of metadata, and that's going to allow us to very quickly recompute the attention matrix during the backward pass without storing it. You can think of this as kind of similar to gradient checkpointing, but it's kind of first class in FlashAttention. And our implementation is a fused CUDA kernel that allows us to go to have fine-grained control of memory access. So this is how we, first I'll talk about the tiling. This is kind of how we do it. So I mentioned that the kind of technical challenge is that we have to decompose the large softmax into smaller softmaxes. So first of all, if you look at the right there, that's kind of what tiling looks like. So we load up one block of Q, K, and V at a time. So we load up from the GPU HBM to GPU SRAM, those orange, compute the block of the output on SRAM, and then output it to HBM. So the way that we wrote it initially is that we have there's kind of a outer loop around K and V and an inner loop around Q and the output. So if you, the way that this kind of works is that you load up a K and a V, and then you kind of loop over Q, compute this little block, write it out to output, and then you load up the next K and V, read out what you just outputted from HBM, compute it again, and then write it back. And what we're actually doing as we do that is that we are decomposing the large softmax of the output into smaller ones. So softmax has this property where if you, instead of computing softmax of the whole row, you can compute softmax over one chunk, then another chunk. And then to get the right answer, you just rescale the outputs every time. And you can look at our paper for exactly what these scaling constants are. So to summarize, what tiling does is you load inputs block by block from HBM to GPU SRAM. On chip, you compute the attention quickly, and then you update the output in HBM via scaling. In the backward pass, what we do is that in order to recompute the attention matrix very quickly, we're going to store the softmax normalization factor. So in the backward pass, we don't even need to do the scaling. We just write down what that final softmax scaling is. So that's one float for each row of your attention matrix, and then quickly recompute the attention from the Q, K, and V inputs in SRAM. So technically, this gives you slightly higher flops than standard attention. So if you look at this table, standard attention will have, in the way that we set it up, it will have 66 gigaflops, FlashAttention will have 75. But because FlashAttention has so much fewer HBM reads and writes, you get a much faster runtime. So in our paper, we also have a theoretical analysis on the I/O complexity, which I'll go over quickly. So for a sequence length n, a head dimension d, and an SRAM size m, standard attention incurs O of nd plus n squared HBM access, while FlashAttention incurs n squared b squared by m. So we were using that SRAM to reduce the amount of HBM access that FlashAttention occurs. So typically the Ds are 64, 128. Your M is something like 100,000. So that's per streaming multiprocessor. And as you can see, as you increase that block size, you see a reduction in HBM access and a reduction in runtime, up to kind of a certain amount of block size, where you start getting bottlenecked by other bottlenecks on the GPU. In our paper, we also wrote an extension to block sparse attention. So I mentioned earlier, there's these sparse and low rank attention algorithms. So we actually have an extension of FlashAttention to block sparse attention, where if you know the sparsity pattern you want to use affixed ahead of time, it's very easy to implement in FlashAttention. What you do is you just skip the blocks that are supposed to be sparse. So here, this changes the I/O complexity. You add this little S factor. So S is called the sparsity fraction. And you see that as you kind of increase let's see, you increase let's say how to say this. As your attention computation becomes more sparse, so more sparse will be on the left side of this graph, you get a much faster attention. And it's almost linear in terms of the sparsity fraction, which is actually quite exciting, because typically you would need to see something like 80% sparsity before you see any speed up if you don't use FlashAttention. Cool. So now I'll move on to the empirical validation. And our empirical validation was really split into three parts. So first, we were benchmarking the attention module on its own. Then we showed some speed up using kind of end-to-end training of transformers. And finally, we used the memory savings to get to longer sequences to get higher quality performance. So first, just some straight up benchmarks of the attention module. So just out of the box, FlashAttention gives you 2 to 4 times speed up, a 10 to 20 times memory reduction over standard kind of Hugging Face attention without any approximation at all. You also see a 10 to 20x memory reduction because the memory footprint is going to be linear in sequence length instead of quadratic, as with kind of a standard attention operation. We can use FlashAttention to get faster end-to-end training of transformers. So I mentioned in the beginning, we set the MLPerf record for training BERT large. So this MLPerf is kind of a highly optimized standard benchmark for training speed. The way it works is you start from a fixed checkpoint, and then you train your BERT model till you get a accuracy of 72% accuracy on mass language modeling, kind of around 8x A100. So this is a benchmark that's kind of each hardware vendor will kind of break their teeth on it to try to show that their hardware implementation is really the fastest. And there's kind of teams of people who are doing this. And with MLPerf, with FlashAttention, we were able to actually beat the previous MLPerf record by like 15% at the time. Now all of these state-of-the-art MLPerf solutions use FlashAttention. We used FlashAttention to speed up GPT-2 training. So this was training on open web text. We reached the same perplexity with much faster training time compared to things like Megatron or Hugging Face. So we get a 2 to 3.5x speed up depending on what your baseline is. We can also train GPT-2 with longer context, yielding higher quality. So here we scaled up at the time GPT-2 small, usually has a context length of 1K. We scaled it up to 4K to get a higher quality model. I think this 4K model actually trained even faster than the Megatron model. So it had a longer context and trained faster and was higher quality. There's also a lot of other, fun applications of high quality. Right, so here's the rest of that table that I just mentioned. So we scaled GPT-2 to a longer sequence, and it was still faster than the Megatron, and it had a higher quality. We also used FlashAttention for long document classification. So here, these are two data sets called MIMIC3, ECTHR. MIMIC3 is a medical nodes data set. ECTHR is a legal documents data set, tens of thousands of tokens. We just extended the sequence length of a pre-trained Roberta model, kind of doing something naive with the positional embeddings, and then fine-tuned them on these classification tasks. And just this simple change led to a kind of 6.1 F1 score improvement on these kind of long document classification tasks. There's this fun little benchmark called PathX that was designed to, it's part of a benchmark called Long Range Arena. It was designed to kind of test the long sequence capabilities of transformers. This task was really designed to push transformers to the limit. So you have images like the one that I'm showing here, and the task is to tell whether those two dots are connected. And the challenge is you can only read this image in 1 pixel at a time. You're not allowed to use patches or anything like that. And so what that means is that for path X, that's 128 by 128, so you need a sequence length of 16K. There's an even bigger version called path 256 that requires a sequence length of 64K. That's kind of what when this benchmark was released, it took 2 years before any model could solve it, and not until FlashAttention. And FlashAttention was kind of the first model that showed that kind of a vanilla transformer, nothing special, just extend the sequence length, can also do all of these tasks. So that table on the bottom left, all those X's either mean the task did not fit in memory, or did fit in memory but never got above 50% accuracy. So a transformer simply extending the sequence length can actually get above kind of random guessing on this task. So FlashAttention yielded the first transformer that can solve path X, and we actually used the block sparse FlashAttention to get good performance on path 256. FlashAttention itself also fit, but I think it would have taken a month or two of training. So block sparse FlashAttention really allowed us to get good performance on that task. Finally, I'll talk about some future directions. I guess as of this presentation, these are actually also past work, but as of relative to when we released FlashAttention, these are kind of some follow-up works, also pushing along the long sequence path. So the first is a paper we released called Hungry Hippos, H3, where we replaced attention with a new primitive called state space models, and we also introduced a IO-aware algorithm to run them. So the background here is we wanted to train language models with much longer sequences, but attention itself was, if you want to get to longer sequences in language modeling, you're still going to be bottlenecked by that kind of quadratic computational complexity in attention. So we replaced attention with a new set of primitives called state space models. So state space models, a couple of things about them. You can think of them as a mix between kind of recurrent neural networks and convolutions. They scale linearly in the sequence length, so they scale. You can get to much longer sequences. So one challenge with using state space models is that previously nobody had showed that you could actually match transformers in quality. So we designed a new state space model layer called H3 that we specially designed explicitly for language, and that actually allowed us to match transformers in quality on language modeling. So that layer is kind of shown on the left, and then on the right hand of my screen, we introduced an algorithm called FlashConv that exploited kind of Tensor Cores on GPU to compute the convolutions quickly, and also exploited the recurrent nature of state space models to scale to much longer sequences. So that's a model called H3 that we presented at ICLR this year. There's another follow-up. This is a paper called Simple Hardware Efficient Long Convolutions for Sequence Modeling, where we were building off kind of the H3 line of work, and we were wondering, can we replace those state space models with something even simpler? And turns out one thing that we can do is just kind of classic convolutions. So these are a kind of a convolutional language model that can match transformers. Also, we can scale it linearly. We have another nice IO-aware algorithm to scale it. And this one we will be presenting at ICML in about a month, actually, at the end of the month in Hawaii. So here it's another approach to kind of getting long sequence and language modeling, and that has a much more simplified presentation where the core model is really that thing that I'm showing on the left, just a raw convolution with learnable convolution weights. You just need to regularize them kind of correctly. So in summary, today I talked about FlashAttention, which is a fast and memory efficient algorithm for exact attention. The key algorithmic ideas are tiling and recomputation, with the upshot of faster model training and better models with longer sequences. Thanks so much for listening today. So FlashAttention was work with Tree DAO, who you can see on screen here. I see somebody has raised a hand. So Arsh, happy to take your question.
Yeah, just wanted to ask you about the alpha and beta parameter when you compute softmax.
Mm-hmm.
So how do we determine those values?
Yeah, so let me. So I don't know. Let me quickly scroll to see if I wrote it down in this presentation. I don't think I did. But so the alpha and beta, this is just a scaling of the existing things there. So if you think of softmax, the way it works is it's a if you imagine the numerator and denominator of the softmax operation, in the numerator there's kind of a you could think of it as a pointwise thing, and then the denominator is kind of a sum of all the inputs, except you have to exponentiate it. So basically what that scaling, it's a sum of the exponents. So what that scaling thing does is it just, if you kind of do some basic algebra, you can find that you basically take what the previous sum was and then what the new sum should be and kind of rescale it appropriately from there. So these alpha and beta are fixed based on your previous inputs and outputs. So they're just literally just some floats that you update as you're updating this computation. It is written in our paper. I don't think I have it written in this presentation, but if you kind of write down how you would kind of rescale something like A over A plus B to A over A plus B plus C, that's basically the rescaling that has to go on. So pretty simple, just some basic algebra.
Yeah, thanks. Yeah, that cleared my doubt.
Yeah.
What I can just quickly say as well is, yeah, thanks a lot, Dan. Really, really well explained. I can jump in with a question as well. Also, maybe Yasser, I don't know if, so I'm actually not on the YouTube one right now, but if there aren't any questions there, maybe there's not, but if there are, then maybe let's get those across as well. But my quick question, also I have to say, yeah, sorry for not showing video, my train was late, so I'm actually calling while traveling. But my question is, so I mean, what do you think? Obviously, against a really naive implementation, there's a huge speed up. It's obviously completely hypothetical, but do you have any thoughts on what you think maybe NVIDIA's was, where obviously you beat it by 15%, so a substantial margin, but obviously there's something beyond the naive approach that was going on there. Do you have ideas about other kind of ways that you could get? Do you think it's like a variance of FlashAttention? Do you think it's something entirely different? Like, what's your understanding of the space around the design space around algorithms for this kind of stuff?
Yeah, so that's a really great question. So I believe that the NVIDIA MLPerf approach fused some of the operations that I'm showing on screen, but kind of not all of them. So it may have fused, I think, softmax and dropout, or softmax and masking. So it fused kind of parts of this operation, but not the whole thing. And so they kind of didn't sort of go all the way in terms of that speed up. Yeah,
makes sense. And I guess also what I'd say again, so for both people, or anyone that's watching on YouTube, and anyone that's on the call as well, obviously, feel free to raise a hand. In the meantime, another one I have, and also actually just another one would be, we are now, so the reading group channel that we have on the Discord is now going to be centered around this week's paper. So if you have any follow-on questions that you kind of read it in more detail, you think about it and have a question, then if you message in the paper reading group channel, then well, either Dan or one of us will kind of chime in and we'll keep the discussion going there as well. That's another one. If you'd rather save your question to do it offline. But another one for me, a little bit more divergent thinking, and we've discussed this already, obviously a bit, Dan. But just like in the design space of algorithms, obviously, like human intuition goes a long way and often goes a lot further than brute force optimizations do. and this is one example. But obviously, just like in the interest of the total design space of algorithms such as FlashAttention, and with works like Alpha Tensor showing that there's suboptimal matrix multiplication algorithms that haven't yet been discovered, that then being applied to sorting algorithms and so on. How do you think about the design space of such algorithms? And do you think, I mean, is this the global optimum as far as transformers on GPUs go? If you went even lower level, like, do you think long term people are going to be finding the corners of this design space, or do you think over time algorithms are going to be helping us, or even totally finding the deeper corners of the algorithmic design space? And how do you think about, like brute force? I mean, brute force is maybe a slightly unfair term, but how do you think about algorithms such as reinforcement learning and what they have to offer in algorithm discovery?
Yeah, so that's a great question. So what I'm excited about kind of in this space, and where I've kind of taken my research agenda since FlashAttention, is actually doing changing the primitives that we compute at all. So I mentioned at the end with things like H3 or the long convolutions, where we are really replacing attention with completely new operations. And kind of the design space of algorithms there, the things they have to keep in mind are, the questions that you can ask are sort of, what is the arithmetic intensity of the operation that I'm looking at? So something like a naive mapmul, like a dense matrix multiplication, has a very high arithmetic intensity. So you can get a lot, kind of very high hardware utilization on modern GPUs. But obviously something like that is going to scale quadratically. So it's really a question. So the questions that I like to think about these days are, what operations are there to look at? What are the variations of those operations? How do they scale kind of in things like sequence length that we care about, and how can you kind of design new algorithms that still have the same quality properties that you like on that we have from our favorite, things like models like transformers, but that have potentially better scaling properties.
Yeah, makes a lot of sense. And again, Yasser's got a question.
Yep, I have a question, and there are lots of questions on YouTube as well, but maybe I could start with questions here. Yep. So my question would be, so since the release of PyTorch 2.0, it was mentioned, and you mentioned it as well, that they're using the FlashAttention custom kernel, but it appears they're also mentioning the usage of Xformer's memory efficient attention. So I was wondering, like, what's the difference between both, and when would one would be better than the other, basically?
Yeah, so that's a good question. So on A100 and newer, the Xformers just redirects to FlashAttention, to our kernel. So on A100 and newer, the Xformers memory efficient call just calls FlashAttention. On older GPUs, so we never implemented a version for V100, for example, but the Xformers folks implemented a version for V100. So they put in a lot of work there, and for kind of older GPUs, the Xformers version will call back to a kernel that's very similar to FlashAttention, but that they wrote themselves. So on new GPUs, on modern GPUs, they are literally the same thing. On older GPUs, they're a slightly different implementation.
Great, makes sense. Okay, I guess we could take questions here first, and then we could look at the comments. So maybe everyone, you could go.
Do you want to? Because I'm about to go through some tunnels. Sorry, do you want to just take the lead on the questions for a bit, Yasser?
Yeah, sure thing.
Thanks.
Yep.
Hello, Dan. So,
hey.
I just wanted to ask this thing. So since PyTorch 2, like PyTorch team has been focusing on more on GPUs that are not from NVIDIA. So AMD has this GPU called MI250. I think it is sort of very high on the raw flops. So do you have any plans around implementing FlashAttention in a way that is accelerator agnostic? Like, I think AMD GPUs would have a similar memory hierarchy, and I'm not sure about TPUs or Habana chips, but do you have any plans of actually extending the FlashAttention to different classes of accelerators, or eventually coming up with a unified implementation of this that works across all of the accelerators? So I just wanted to.
Yeah, so that's a great question. Sorry,
No,
was there
that's all.
something else?
No,
Yeah,
that's
I believe the AMD folks have a version of FlashAttention that they're working on. I personally don't know much about programming on AMD. I think some folks at Google also have a version that they're working on for TPU, but I don't know much about coding on TPU either.
so it's
Yeah.
actually
So I think
like,
there are versions in development. Yeah.
so it's like the FlashAttention is actually the IO aware part is currently is tested with NVIDIA GPUs and their memory architecture and the hardware function it supports on the A100s, right?
Yeah, so the kernel that we wrote is written in CUDA for the NVIDIA GPUs. I believe that the AMD folks are working on their own version, but obviously with kind of AMD programming and AMD support.
Yeah, makes sense. So thanks.
Yeah, I guess you could go, Vatsalya.
Yeah. So just a quick question. So is it fair to assume that if you can't fit the data into the SRAM efficiently, then FlashAttention wouldn't be super useful in terms of like HBM improvement?
Right, so that's a great question. So the way that attention is computed these days is that you have attention split across multiple heads. So we support up to head dimension 128.
Right.
That's kind of what you can fit on GPU SRAM. On A100, I think on A100, the SRAM size is exactly the same, so it's also 128. So if you have a attention that has a higher head dimension, then you need to do other things. But
Yeah.
most transformers out there only have head dimension up to 128.
Yeah. So do you think like there's generally a way that FlashAttention as a whole could be improved to deal with like this edge case? Maybe not, because like the design relies on SRAM and stuff. But
It may be possible. It would require kind of very careful, SRAM. Sorry, it would require like a very careful pass through the kernel to see if there's any other savings from SRAM. But I think it's pretty close. And I won't say it's not possible, but it would be required skill.
yeah, makes sense. Thanks. Thank you.
We should maybe go to the YouTube question just for some.
Yeah, I guess we could jump into the YouTube questions. So let's see. So there's a question here. Is FlashAttention more about helping with memory constraints? I guess the person is trying to ask whether it's more like, is it concerned about reducing the memory footprint more or making the attention operation faster?
Both. So we get 2 to 3 times speed up and a reduction of memory footprint from quadratic to linear.
Yep, makes sense. There's an off-topic question here. Tips on getting started with research and coming up with ideas.
Yeah, so this is a great question. I think now is kind of the best time in at least as long as I've been doing research to get into research. Like there's so much excitement, so many exciting things to do. I'd say if you're just getting started, like just build interesting things and find interesting things to do, and do things that you're personally interested in, and just pay attention to what in my current process is stopping me from doing something that is more exciting, or stopping me from doing something that I would like to do. And then if you identify those things that are kind of informed by real problems, real questions, then that's kind of a great signal that maybe you've hit on some really interesting question that if you solve it could be really interesting. I think for research in particular, finding a good research mentor is important. I think there are, if you're at a university, then there's, you can reach out to professors who have done work that you're interested in. If you're not in a university, I think there's there's these programs like I want to say like ML Collective, and I think Cohere has something like it too, where you can kind of get into research if you're kind of a junior person. I'm less familiar with how you get into research in industry because I haven't been there before, but I think there are kind of pathways like that.
Yeah, great answer. There's a question here about the H3 layer, the layer with the very interesting name. Are the state space models based on the same concept that is used in signal processing? I'm not sure if I get this question, but maybe you do.
Yes, yeah. So so to give some background for everybody, so a state space model or state space representation, it's an ancient idea from like the 60s. It's used in signal processing a lot to kind of process time series. We don't quite use it the same way that they do. Like the traditional way that you would use a state space model, you'd be like saying, I want to analyze, I don't know, earthquakes or something, and then I'm going to say that based on the composition of the rocks and whatever. Okay, I'm not an earth sciences person, so take what I said with a grain of salt. Like based on those things, you would kind of design a state-space model that sort of matches what you're seeing. The way that we use it, we use the same basic kind of mathematical structure, but we learn the parameters from scratch. So you can think of it as, language is kind of this amorphous signal over time, and we are learning state space model parameters that would allow us to do something like next token prediction or math language modeling.
Yeah, I hope this satisfies the person who just asked. There's a question here. You mentioned that there are fewer read-write on HBM in FlashAttention. So when you compute one block on SRAM, are you not writing back on HBM block by block? Can you explain this? This is the question, basically.
Yeah. So So to answer that question, so within each loop over the if you kind of imagine that tiling block, we are looping over K and V in the outer loop, and in the inner loop looping over Q. That was just the way that we wrote it the first time. There's another version that switches the order of the loops. But you're right that every time we loop over Q in each of those blocks, we're going to write something down to HBM. And then when we go to the next block in K and V, we're going to be kind of reading that output to update it. But this is going to be reads and writes that are just over like this little block of the output at each time. If you switch the order of those loops, you can get it to the point where you are just kind of computing, you're holding the whole output in SRAM the whole time, and then you just write it out at the end. I think it gives you a slight speed up in the forward pass, but it's about the same in the backward pass. We have in the FlashAttention repo, we have a Triton kernel that does it the other way. It just so happens that when we first wrote it, when we first wrote the CUDA kernel, we did that particular order of looping.
Yep, makes sense. Let me see if there are any more questions.
Yeah, we want to forget. Oh, is there another one? Oh yeah, Harris has a question. Yeah.
Yeah, Harris raises his hand.
Yeah. Hey Dan. So we talked about FlashAttention and how it's designed around handling long sequences and capturing more context. But I was just curious, how does FlashAttention stack up against the conventional attention mechanisms in terms of like smaller length of sequences or smaller batch sizes?
Yeah, so for smaller sequences, it's also faster kind of throughout. I think in our paper, we have a graph that shows speed up versus sequence length. Or if not, it's in one of the tables in the appendix. And it's kind of faster throughout because even the basic, even for short sequences, the entire operation is bottlenecked on just those reads and writes. Yeah, so the whole thing is it's faster kind of across the board as well.
Yeah. Okay. Thanks, Dan.
Yep.
Are there any other questions on YouTube at all, Yasser?
There are like 2 more, I guess.
Okay. Yeah, we can go through those maybe. We've still got a bit of time.
Yeah, I mean, one of them is, will the slides be shared?
Oh, yeah. I guess Dan's happy to share them. Is that okay?
Yeah, I can share them.
Awesome. Sounds good. We can put them somewhere. Yeah, and then the other one.
Yeah, I guess that's mostly pretty much it. We could probably continue the others in the
Yeah, well, exactly.
Discord.
So I have I have one more. It's a bit more kind of I don't know, kind of big picture. But so do you see, obviously, as it's becoming clear that you don't necessarily need big dense matrix multiplications to do AI training, or certainly not inference, and obviously things like, well, quantization, sparsification, pruning, model distillation, etc., can all get very, very good performance from much more memory efficient models. And particularly with things like tensorization, and when you have sparse tensors and stuff, it does obviously lend itself to a different hardware architecture that might not just be obviously GPUs, which were originally for just doing dense transformations and stuff in graphics. And there's things like Grace Hopper coming onto the scene, and there's a lot of work making hardware that doesn't just do dense matrix multiplications well, but it does sparse stuff very well as well. So stuff that's mathematically simpler should also, in theory, be runtime more efficient, and often that's not the case, obviously, with conventional hardware. How do you see the interplay between hardware that takes steps towards algorithms? So obviously the algorithms derive AI, and the hardware tries to catch up with that, and then often you do the inverse, which is you then try to make algorithms that kind of work well on the hardware and everything. How do you see those two interplaying? Basically, it's a pretty open-ended question, but as hardware tries to take directions in what's actually mathematically better, and the other happens as well, do you think things like FlashAttention and that kind of insight will happen more, happen less, or will it just be inevitably like implicit in the hardware design that things are efficient anyway?
That's a really, really great question. I think hardware software co-design here is really interesting to think about. Certainly over the past, let's call it five plus years, there's been a drive to get kind of more and more matmul flops. And there's a good reason for that, for kind of very fundamental hardware reasons. Kind of doing kind of a systolic array computation is the best way that we know how to get a ton of flops into your hardware. I think as we explore new things like H3 or long convolutions for language modeling, there may be a world where we could have radically more efficient models. And that world may look different in terms of what hardware you want, or what's the best hardware you need. Certainly, we're not in that world yet, but as things evolve, as we continue to do research, things may change. So I think it's a really interesting question. I wouldn't be surprised if for the next while, systolic arrays are pretty hard to beat in terms of just hardware design, but there may be, as AI evolves, as we change our models, there may be different primitives that you kind of want to bake in to the hardware itself.
Yeah, it makes a lot of sense. I also don't think that dense arrays are totally disappearing anywhere anytime too soon. It makes a lot of sense. Awesome. Also, sorry, I've been a bit intermittent, but I'm now in a stable place, so I can tell my camera on and everything. Abhimanyu, you got another quick question?
Sorry, it's for this. So I had an interesting doubt. So recent NVIDIA GPUs have this thing called Tensor Cores. So they basically trade off accuracy for speed. So
sorry, what was the word that you said? Tensor something?
Recent NVIDIA GPUs have this thing called Tensor Cores, which actually trade off accuracy for speed of computation. So do you think
Tensor Cores was that?
Yeah. So is my audio actually lagging or something? Hello.
I believe Tensor Cores are.
Hello.
So can you continue with your question?
Sorry, what was the question about you again? Sorry, go ahead.
So I was saying NVIDIA GPUs have this thing called Tensor Cores, which actually trade off accuracy for compute speed. So do you think like would it be possible to actually implement FlashAttention that just exclusively uses these cores, because they actually have like a lower accuracy when you're doing operations on them, but they are much faster? So
so I think I didn't include this in my slides, but tensor cores are how modern GPUs, or how NVIDIA computes matrix multiplication. I think maybe your reference to lower accuracy is maybe referring to things like FP16 or BF16. And here, so FlashAttention is actually only supported for FP16 and BF16. And we use the tensor cores to do the kind of QKV operations. It's kind of a, it's a fundamental part of how attention is computed. And is one of the reasons why we didn't write a kernel for V100, because the V100 tensor cores are a little bit older, the interface is a bit different, and they're a bit slower, or smaller rather, compared to, for example, A100 tensor cores and H100 tensor cores. So we use tensor cores in FlashAttention. We use the half precision versions to get the speed up.
Okay, that makes sense. Thanks.
Awesome. Cool. Okay. Well, I guess in the interest of time, I think we're pretty much there. So I guess now's a good time to wrap up. But what I can say again is thank you very much, Dan. For really awesome to have you here to kick off our series. Excited for many more. We'll be doing one of these every week, partly with guest speakers, partly with some of us in the team presenting various papers that we've selected. We've actually already done a few of them that we'll be then retrospectively uploading into the series, and we'll start doing them live every week. So everyone in the community is welcome to get involved, ask questions, and everything. Really interesting discussions following off at the end as well. What I'll say as well is that we have the machine learning reading group channel in Discord. So if there's any follow-on questions about this paper, the idea is that every week we have paper-specific discussions. So this week, the discussion is, of course, on FlashAttention, and then next week it will change and so on. So yeah, if there's any other questions, feel free to ask in the Discord. One of us will try and answer. Maybe we can get Dan's thoughts as well. But yeah, otherwise, thanks again, Dan. Thanks everyone for listening in. Hope everyone has a good evening, and yeah, see you guys all again soon. Thanks a lot. Bye-bye, everyone.
Bye-bye.
Thank you. Bye-bye.